You said to know.
Yes. Number 54 on 1.4 was this. That was the thing with the height and the velocity equations, right? The height of a ball. Now, you do not need to memorize those formulas. It would be like number 54. Problem 54, what page is that?
46.
Page what?
46.
On page 46, problem 54, they give you each equation. But what I want you to be able to do is when you look at that equation, know that the 38 is the initial velocity. I want you to know that the 74 is the initial height,
Yep.
right? But you won't have to write the equation. It'll be given to you, okay? So what else about that one? So in that problem, it asks, is the ball going up or down at 2? So what you would do is plug a 2 into the velocity equation, right? And it's negative. And since the velocity is negative, if we look at our chart, if the velocity is negative, the velocity is negative, the height is decreasing, right? Yes.
Maybe a silly question, but like, you know how you asked, you were doing part C, like what's the ball's height? Is it increasing or decreasing at time equals 2, right?
Right.
So, you put into the velocity graph, like, or the velocity equation. How do you exactly know like which one? Because probably for mine, I think that the H.
Well, here's why. You're right. They asked about the height, right? But the problem is if you plug a 2 into the height equation, that's going to just tell you where it is. That's going to tell you its height. It's not going to tell you if it's going up or if it's going down.
Okay.
Right? So if you plug a 2 into the height equation, it'll tell you where it is at 2, but it won't tell you which way it's going. And so again, that's where it comes to the chart. This is like the height and this is the velocity, right? The velocity is like h prime. So if I want to know when the height is going up, I want to see if the velocity is positive. Or if the height is decreasing, I want to look and see if the velocity is. So that's why we plug it into velocity. You're right. One of the next questions says, when does it hit its maximum height? Well, again, you might think you would plug it into the height equation. No, its maximum height is when what? When its velocity is 0, right? So you would take the velocity equation, set it equal to 0, and solve it. And it comes out to like 1.188 or something. That's the time when it's hit its maximum height. Then I think the very next thing it says is, how high was it then?
How long was it? Oh,
Well, part of that same thing, it says how high was it at its maximum height. That's when you then plug that number into the height equation.
The number that you got from the velocity.
The number you got from velocity, you plug that into the height equation and see how high it was.
So since we're kind of still going, like, how long was the ball in the air? How do we do that again?
And then how long was it in the air? Well, it's in the air until it hits the ground. So that's when its height is 0. See? When it's hit its maximum height, it's when the velocity is 0. But when it hits the ground is when its height is 0. So you take the height equation, set that equal to 0, and solve that. And that was the stuff we said you might need to use a calculator on. You could use the solve thing on your calculator, and you could. That's the one part of the thing you might use your calculator for. The other comment I would make would be about the zooming. Somebody asked about that in the other class, and about the zooming in. And we did that a couple different ways. One way, if it's just a picture like this, you can just draw a tangent line and do a slope triangle. That would be kind of like zooming in, finding the slope of a line like that. And there you'd have some leeway. You know, you would say, well, you go over 1, you go up about 0.6. Well, if it's 0.6, I might take anything from 0.4 to 0.8, or you know what I mean? I'd give you some leeway in there, where you would actually draw your line. But if it's a calculator one, that's where we would just pick 2 points really close. Pick 2 points really close to do the slope. So if you wanted the slope at 2, you might plug in 2.001 and 1.99 and just do a slope.
We could do it either way,
Either, as far as this, well, it would depend on the problem. In a no calculator situation where I just give you a picture and ask you for the slope at 2, you would do this. You would draw a line and you would kind of do a slope triangle. If it's a calculator situation where I give you an equation, right, and ask for the slope, then it might be pick 2 points and plug them in. But that's about all we did in section 1.5. Is that okay? Brittany, anything else? Okay. Anybody else have any other questions on the homework question. You guys just yell at me when you're ready to go into start. Okay.
Let me this up on
Okay. Well, that way we can start you guys. Okay, anybody else have something before
29.
29 on today's, right?
Yeah.
Okay, so that would be the thing with the cone and the height and those things.
It was really just B that I needed help with.
Yeah. Here's the main thing on that. You had a cone and you have water filling up the cone, right? Now the water was pouring in at a constant rate, which means that the volume graph would be going up in a straight line there. But the height equation would be like that, right? Because as the water comes in, like 1 gallon would fill it up this tall, but the next gallon wouldn't fill it up as high because it's spreading out, right? It's spreading out. So it's not going up as high. So the height is actually leveling off. Now the questions ask about H double prime and V double prime. Okay? That's the part you're asking about. Okay? Well, what does the chart tell us about the second derivative? It tells us concavity, right? Concavity. Second derivative positive, concave up. Second derivative negative, concave down. So on these two graphs, what's the concavity of V? It doesn't have any concavity, right? So therefore the second derivative would be 0. And this one is concave down, so the second derivative has to be negative, right? Because of the, so you had to first understand what the V and H graphs would look like.
So we have to.
Well, it said something about units. You didn't really have to draw them, I don't think. We talked about units. I mean, this could be cubic centimeters, and this would be cubic centimeters per, I don't know, what was this, time? Was it time? Cubic centimeters per second. Yeah.
I know I had asked about this morning, but we need to do
Okay. I think it might be worth, are you talking about on the review ones?
Yeah, on the review problem.
Okay.
It's like one at the beginning.
Oh, on page 75 she's looking at. Okay. Well, I wish I had it. I might have a graph. Let me see if I have a graph of. '41 and '47. No, I don't have a picture of that. Okay. 41, it says that 2 is a local max of G and 3 is an inflection point of G. Is that the one you're talking about?
Yeah, just a minute.
Yeah, so could G of 2 equal 1? Well, yeah, just because it's a local max, it could be anywhere. G of 2 could equal 1. But could G prime of 2 equal 1? And that's no, because at a local max, what's G prime have to be? G prime has to be 0, right? And could G double prime be 1? Well, on a local max, what's G double prime got to be? What? No. If G has a local max, what's G double prime? Yes, right? At a local max, what's the concavity? Remember, second derivative means concavity. At a local max, it's concave down. So G double prime's got to be negative, right? So it couldn't be 1, right? That's kind of what that question gets. So some of you haven't done the review yet. You're going to get into those. There are a little bit different ways of asking these same kind of questions. And then on 47, that was at speed limit law. They give you the graph of F prime. And so from 2 to 3, that F prime graph they give you there is positive. So the graph's got to be going up. So it couldn't have went down to -6. That's what we were talking about. While we're there, we might mention, this would be good for everybody, because I wanted to mention this to everybody anyway, number 80 on page 76. If everybody would just look at page 76 and read number 80 real quick. Because this is something that I had said I would ask of you way back when we started this in section 4. Number 80 on page 76. Just read that. Okay, anybody want to take a crack at that? Brittany, go ahead.
Is it that the slope of C at 23 degrees is negative?
Okay, that wouldn't be quite enough because you use too much math stuff and not enough in context of the problem. You did get close when you said the 23 degrees, but we need more. We need more of the real world language, not math language. Okay, somebody else want to fill in what she said?
Cost is decreasing.
The cost, C is the cost, right? So we got C and C prime here. So if we go back to the chart, we got C and C prime. And, oops. So what they told us there is C prime is negative. So C is decreasing and C is cost. So go ahead.
Well, no, you.
Okay, so Sam, go ahead and tell me the whole sentence there, you would say.
What do you mean, like?
Well, you said the cost is decreasing, but I need more. I get the 23 in there, get the negative 0.17 in there, get all of it in.
Okay, so the cost is decreasing at a rate of negative 0.17.
No. You don't want to use the word decreasing and rate. Well, it would be a rate. I mean, get the units in. Keep going. Okay, cost decreasing
Negative 0.17 at each time.
0.17 what?
Cents or 0.17 dollars. It'd be 17 cents. I
Be
guess.
17 cents.
Per 23
No.
days.
No, the 23 isn't days. Brittany had that right. What's the 23? Okay, Ty, you want to try it from the beginning?
So, at 23 degrees.
Perfect. That's a perfect start. At 23 degrees, right? We're talking about instantaneous rate of change, right? So at that is okay. At 23 degrees, go.
At 23 degrees, the cost is decreasing at point or negative at 0.75.
0.17 or 17 cents per day. That's where per day can come in because it says C is cost in dollars per day. So C is dollars per day.
So it's
Right.
already a prime derivative.
So the derivative is negative, tells us the cost is decreasing, right? But it's at 23 degrees. So there's two things to get in, the input and the output, okay? So when it's 23 degrees outside, that would be better than just saying at 23 degrees. I said that's perfect. Okay. At 23 degrees outside, when it's 23 degrees outside, the cost to heat your home is going down by 17 cents per day. Or you could say it's 17 cents cheaper when it's 23 degrees outside than it was when it was 22 degrees outside. You might say that, right? Okay? Because we had talked about that. Remember we were doing Bismarck, at 2 o'clock, they're going 70 miles per hour to the west or whatever. We want to be able to talk about those things in the units of the product. Okay? So that's one to look at. I think there's another one or two of those in there where you could practice it too. Okay? Ready? Sort of, kind of. All right. Make your calculator. Okay, the rest of you,
Or we probably have to be that low.
yeah, we put the hats on. It'll be easier for me to take you back out. Well, no, not really. Well, leave. That's fine. The rest of you can go ahead and start working wherever. I've got a little other review thing I want to do. If you've got another question you want me to answer, we can do that then too. Okay? But I just want to do some chart review with this graph here in a little bit. So we can go ahead and work and figure out what other questions you might have.
If you have lead, yeah. I know it's out of lead. Only one pencil is yeah.
Figure out right now.
Oh. Oh yeah, pens. But I can't even find my actual sense of it.
How did it back? Okay.
Oh, there you go.
So we're just going to repeat it.
Yes.
I'm not gonna see it.
You know what?
We didn't have any last session. What?
We had a test.
Oh, yeah. Well, we should-
Basically, she's gone. Rock step back. Basically, we're gonna be gone. Watch the internet.
What if I'm gonna read it?
You're gonna be there. Yep. Okay. So, no. Is that maybe? That's kind of my like assumption. On why you're using these things. Yeah, I like it.
Okay. Anybody have one right off the top of their head here that they got a question? We haven't done it. Okay, well, I'll give you more time to think about that. I want everybody to look up at this graph that I got right up here. Okay? Okay, now, just, oh, somebody, that comes up, just say, okay.
Okay.
All right, so I want you to look at the graph we have here, and I want to just ask you just a series of quick things that I think would be, I think will be helpful. All right, so let me go back a page where we're at. Here it is. Okay, so let's pretend that this graph right here is f prime. Okay, this graph is f prime. Now, you might want to have your chart in front of you. If you could do it without the chart, even better. Okay, but you might want to have the chart in front of you. And I'll maybe flip-flop back and forth between the chart now. All right, now what I've labeled here are different points. A, B here is an inflection point. C is a root, local min, inflection point, local max, inflection point, local min, and root, right? Okay, so let's say that's the f prime graph. Where does f have a local max? Now, don't answer it right away. Let's just give everybody a chance on all of these. Give everybody a chance to think about it. So when I ask the question, don't say anything, just think about it. And then I'll say go, and then you can just say it. All right, so where does f have a local max? Could be one or more places. Go.
C.
Because?
F prime changes from positive to negative.
And you might have to justify your answer on that one. So the justification would be, since f prime changes from positive to negative, f goes from increasing to decreasing, right? That's why there's a local max at C. All right? Where does f have inflection points? Think about that a second. Where does f have inflection points? Go.
A, D, F, H.
A, D, F, H. Because according to the chart, and again, don't be afraid to ask questions here now on this, but F has an inflection point when these two categories switch. So F prime has to switch these two. Has to go up to down, down to up, which is a local max or local min, which is an A, D, F, and H. All righty. Where's F increasing? In what intervals? Between what two sets of points is F increasing? Go. A to C. And couldn't you say E to infinity, right? You could keep going, right? Even though H is 0 there. So from E on, whenever this is above the x-axis, positive, right? All right, one more with that.
Can you count H for that? Like.
Yeah, I would say from E to infinity. Because it's, to be increasing, really it needs to be greater than or equal to 0. So it can be at 0. Where is F concave up? Where is F concave up? Go.
D to F, H to
D to F, H to infinity, and then if you count any back here, right? F is concave up when F prime is increasing. All right, very good. That is a big part of the quiz, those kind of questions. Hopefully you find those easy. Those are also the ones we talk about sometimes where if you get off track, you can miss a whole bunch of them in one section. So, but don't freak out about that and don't overthink it. Okay, don't overthink it. If that's what you're seeing in the chart, the way you guys are shouting them out at me, you seem pretty confident about it. Okay, and that's good, and you should feel confident about it. But be careful that you're just not getting off track, that you're thinking about the right graph and the right thing. Okay, so let's change this graph to be F double prime now. Let's make this graph be F double prime. Where does F prime have a local max? Go. And you weren't as confident about that one. Where does F prime have a local max?
C.
It's the same question, isn't it?
Same thing.
It's the same question before. I gave you an F prime graph, asked you about F. Now I gave you F double prime and asked you about F prime. That's the same relationship. It's the same question. So when I come over here and I look at the chart, where does F prime have a local max? It's when F double prime changes, it's when F prime goes from up to down. So therefore, F double prime has to change positive and negative. It was the same connection we looked at here. Okay? So all of these would be the same if I did that, right? If I asked where does F prime have inflection points, it would be at those same places. Okay? F prime would have inflection points when F prime changes concavity. Well, it's going to change concavity when this goes up and then down, which would be at A and D and F and H, right? Those would all be the same questions and the same reason. All right, so let's ask a few other different things. Okay. Where does F have inflection points? Where does F have inflection? Where? Go ahead. Go.
C.
C and E. I can't tell if we were confident of that or the ones that were confident just were a lot louder. But where does F, remember F double prime mostly tells us about concavity of F, right? So F has inflection points when these two columns switch. So those inflection points are when these two columns switch. Positive to negative and vice versa. Well, that happens at C and it happens at E. Now what would H be on F? No, we often think flat spot. That would be a flat spot on F prime.
Yeah.
On F, F double prime goes positive to stay positive, all that means if F double prime is positive and stays positive is that F is concave up and stays concave up. Okay? There's nothing on that. You wouldn't even notice it. It would just continue to be, there wouldn't be a blip, there wouldn't be anything. It would just still be concave up. Okay? But C and E would be inflection points of F. Where would F be concave down? In what interval? Just don't say it right away. Where would F be concave down? Where would F be concave down? Go.
C to E.
C to E. When F is concave down, F double prime has to be negative below the x-axis, less than or equal to 0. Now you could argue we wouldn't include C and E because when F double prime is 0, then F wouldn't have any concavity. Okay. Well, if it's switching, there it is. All right. So one more change, and then we'll do some work. Now let's say that this graph is F. This graph is F. Where is F prime greater than or equal to 0? Where is F prime greater than or equal to 0 on this F graph? Go.
D to F, H to
D
infinity.
to F, H to infinity, and that little piece there. F prime is positive when F is increasing. Okay? Where does F prime have a local minimum? Where does F prime have a local minimum? Go.
B and
B and G. That was a tricky one, wasn't it? B and G. Now, not if you have the chart in front of you, right? The chart, this is one like this is where the chart can become very helpful. What do you need? What does F prime look like if it's a local minimum? If F prime's a local minimum, what's that look like? On F prime. What's a local minimum of F prime look like on F prime? Like a U, right? It goes down then up. It goes down then up, right? So to be a see, we can't just say where F has inflection point, right? A local minimum of F prime here says it's a possible inflection point. So you can't just look at the inflection points because you guys skipped E, right? You guys told me just B and G, correct? A local minimum of F prime means it goes down then up. So F has to go concave down, then concave up. So at B, concave down switches to concave up. G, concave down switches to concave up. But at this one, it switches concave up to concave down. So you switch concave up to concave down, this graph is going to go up then down, which means that'd be a local max. F prime would be a local max. Okay? So that was kind of tricky. Tricky there. All right? And then one last one. Where is F double prime? Well, let's do two of them. Where is F double prime negative? Where is F double prime negative? In what intervals? Go.
For A to B.
A to B,
E
E to G. Concave down. F double prime is negative when this graph is concave down. So we look for the intervals where it's concave down. Now what if I said where is F prime D? Let's do one last one. Where is F prime decreasing? Same places, right? F double prime negative are the same places F prime is decreasing, which are the places where F is concave down. Okay? So, just a little exercise here in the various different graphs, because there'll be several of those on the quiz where one time I might give you the F graph, one time I might give you the F prime graph, one time I might give you an F double prime graph, and ask you those various questions. Okay? And so that's just a way of looking at that and gathering that information. Okay? All right. So that leaves us half hour or so. You can work on those review questions. I told you yesterday the review questions you probably want to focus on would be from 14 on. 28 through 33 are some good speed limit stuff. 41 through 46 is a good little section that kind of makes you think a little bit. Brittany asked about it, so we were talking about it already. 47 through 51, and that's another speed limit law situation that can make you think about those things a little bit. Otherwise, now, I'm not saying that these problems, 14 on, I mean, the review problems, that doesn't mean that encompasses everything. I mean, that's one of the reasons I kind of talked about 54 and that thing. And, you know, I kind of went through this chart and so forth. I mean, there's some good review problems, but I don't know that if you said, hey, if I do all of 14 on the review, that's it. That's the whole quiz. No, I mean, it's all the stuff we've been doing, right? It's all that stuff. But, boy, I think we've hit on most of that over the course of, all these days. So. Okay? All right, go ahead and get to work, and you can ask me questions. I have more of these matching things if anybody missed out on an opportunity to get that, but you can just go to work.
What's your good speed limit ones?
28 through 33.